Hello guys, in this video we are going to solve this problem 2 from Izho 2010. I'll put the link to the paper in the description. So yeah, okay. So in 1916, Tolman and Stewart carried out their famous experiment providing that the electric current in metals was caused by freely moving electrons. The sketch of the experimental setup is shown on the left hand side. A long coil of radius r and the length h has an inertia moment J0. The coil is reeled up by a single layer of metal wire of length L and mass m, such that number of loops on the unit length equals n. The both ends of the wire are braced to the galvanometer by sliding contacts. The coil together with the wire is set rotating with the angular velocity omega naught, and then the friction force with the torque m is applied to stop the coil rotation. The total resistance of the circuit is R and its capacity is assumed negligible. So basically what we are analyzing here is that the electric fields and effects of the electric fields and magnetic fields produced by simply mechanical means or simply by moving the charges. Okay, so yeah, in the first part we have to determine the total moment of inertia of J of the coil together with the wires. So yeah, it's very simple. It's equals to J equals to J naught plus m r square, because all the mass of the wire is at a distance r, and each small part will contribute to its mass times the r squared. So yeah, it's just J equals to J naught plus m r square. For part 2, determine the dependence of the angular velocity omega at t of the coil on time t. Express your answer in terms of J, m and omega naught. So yeah, in this what we'll do is the torque, which is m due to the friction, will be equal to J times alpha. Alpha is here the angular acceleration. So yeah, here we get the alpha equals to m over J equals to minus d omega by dt, and integrating here, and so we simply get that omega equals to omega naught minus m by j times t. This is up till time t less than up to the time where the coil stops, which will be j omega naught by m. Yeah, and after t, when t is greater than j omega naught over m, the omega will simply be 0 as it's at rest. Okay, so this was part 2. Then for part 3, determine the dependence of electric current strength I as a function of t. Okay, so in this part what we can observe is that just after the coil stops, the electrons won't stop moving, and they will face a resistive force which will be equals to mass times acceleration in the opposite direction of the acceleration of the coil. So what we get here in part 3 is, let's say the acceleration is equals to alpha times r. By this, the force on the electrons would be me times a, which can be considered as E times the electric field, which can be considered as an electric field. So here we get that E equals to m mass of electron times a E. So the EMF induced in the wire will be equals to MEA L over E. Okay, and this will be equals to the current times the resistance equals to I times R. So yeah, we get the current as ME times AL over E. And finally, substituting all the values from part A, part 2, we get that I equals to M E R L over E J R. And observe that this again will be only till time t less than equals to j omega naught over m, and after t equal to j omega naught by m, the current will reduce to 0. For part 4, during the experiment, the galvanometer has registered the electric charge q passed through the circuit, and we have to find the charge to mass ratio of the electron in terms of the given quantities. So what we'll get here for part 4 is the charge q equals to I times t. So current is equals to m times r l over e j r times time is, as we found out in this part, it is j omega naught over capital M, j omega naught over capital M. So M cancels out here and j also cancels out, so what we can get from here is E by me, charge to mass ratio, equals to me r l omega not, sorry, the m is not here, and over rq. So yeah, this is the charge to mass ratio required in this part. So yeah, the 4 parts are done. Now for the part 5, 6 and 7, we have to take into account the inductance of the coil. So for part 5, we have to find the maximum electric current strength Imax in the coil. Now this time, as we are considering the inductance, first of all, the inductance of a coil equals to mu naught n square I into A, which is pi r square into h. And after that, the expression we can get here is L di by dt plus I into R equals to minus E EMF, and this is the simple Ohm's law for that circuit, equals to M E into A L over E, which, from here, and here we are only worried about the magnitudes, so let's just ignore the signs. And at the time of maximum current, di by dt, this term will be 0, so this implies that the maximum current will be MEAL over ER, which, and in the end it will give us Imax equals to ME RL over EJR. So yeah, this will be the maximum current which has been asked in part 5. Yeah, and find the maximum energy W naught stored in the coil during the experiment. Now this is simply half Li square. So yeah, half Li max L into I max square. So energy maximum half L I max square, which in the end gives us the answer of mu naught pi h by 2 into nmme into r square L over ejr. This part is just simplification, so I skipped this. So yeah, this is the maximum energy. And now for the last part 7, in this they have first defined the first they have defined some quantity, which is the fluxes of the electromagnetic energy through the unit area is determined by the Poynting vector, which is perpendicular to both electric and magnetic fields, with the module S, or the modulus of which is S equals to 1 by mu naught EB sine alpha, where E is the electric field strength vector, B is the magnetic induction vector, and alpha is the angle between them. Find the electromagnetic energy passing through the lateral surface for the time period while electric current increases, and the electromagnetic energy W dash passing through the lateral surface for the time period while the electric current decreases. So for this, we will need to find the E and B at the time of changing currents. So first of all, the magnetic field at any time inside the coil equals to mu naught n into I, right? And now, by Faraday's law, we can consider a EMF. We can first consider a loop of radius r, and the EMF generated in that loop will be equals to E, the electric field at the position of the loop, at the r, and E times 2 pi r will be equals to minus d phi by dt will be equals to d by dt. Again, we are only concerned about the magnitudes, so I will just ignore the signs. Will be equals to b times pi into r square. Okay, and so what we can get from here is that E equals to R by 2 times di dB by dt, right? Because pi r square is constant, it comes out of the d by dt, and from here substituting b equals to mu naught n I, we get that r by 2 times mu naught n into di by dt. This is the electric field at any time t. Okay, and what we can observe here is let's say this is the coil. So and the magnetic field will be directed along the coil, and the electric field will be along the tangent to the circle. So these two are in effect perpendicular. So what we can see now from the expression of the Poynting vector here, this s equals to 1 by mu naught eb sine alpha. Here alpha is 90 degree. So now finally we get that s equals to 1 by mu naught into e into b, which will give us mu naught n r by 2 into mu naught n I into di by dt. So finally mu naught get cancelled. So here we get that mu naught n squared r I by 2 di by dt, and the total flux passing through the surface, cylindrical surface, can be given as s dt. Integrating this equals to mu naught n square I r di by 2, integrating from I equals to 0 to Imax, and integrating flux from 0 to s. Oh, sorry. We get that s equals to s equals to mu naught n square. This integrated will be I square over 2. So it's mu naught n square r I square by 4. Right? Yeah. Okay. So this is the total flux which has passed through time t through a per unit area. So the total flux will be, or rather the total energy uh, will be this times the surface area of the cylinder, which will give us s times 2 pi r h, which is mu naught n square r I squared by 4 into 2 pi r h, and this finally gives us mu naught pi h over 2 times n m m e r square L over E j r whole squared. So this is the total energy which is transferred while increasing, and obviously this will be equal to W will be equal to W dash, because from here we can observe that the total energy which has entered the system while increasing is exactly equal to the maximum energy which is being stored, right? So and this energy will again will be lost, because in the end the energy is zero. So so we can clearly see that W equals to W dash again here from here. So yeah, that's the final answer. So yeah, this finishes our problem. So thank you for watching.